What's up, boys and girls? This is your favorite neighborhood evil genius, and this is part 2 of chapter 1 of Fundamentals of Plasma Physics by J.A. Bittencourt. Part 2 of the chapter 1 problems. So let's jump right into where I left off. I'm going to go into problem 1.4. I know I'm skipping problems. I skipped problems 1.3 because it's more chemistry than it is anything else. We might go back into that. Well, it's chemistry and a little bit of nuclear physics. That's another book that I actually want to do. I have a nuclear physics book. I don't think it's very good, but it's a good. But it has some good problems that illustrate nuclear physics fairly well. It's not very comprehensive, but anyway, plasma physics. So problem 1.4 asks us to calculate the Coulomb repulsion force and the associated electric potential energy due to the Coulomb interaction of two deuteron nuclei when brought together at a distance 10 to the minus 14 meters. And so first and foremost, what is a deuteron? A deuteron nuclei is one proton and one neutron. I guess the best way to think about that is a helium ion. Yeah, helium ion. And so the total charge is E because the only nucleon with a charge in the deuteron pair is the proton. So the force Coulomb of the deuteron charge, or the two deuteron atoms, is first and foremost the music in the background. It's from Pokemon Sun and Moon. I think it's called the Shadow of the Aether Foundation. If anyone's interested. So 8.99 10 to the 9. That is the electrostatic force constant times 1.6 times 10 to the minus 19 squared. So last problem that we had, the first problem that we had something on the lines of an e squared in the denominator of one of those problems. So I was right, and there was 10 to the 38 over the force squared. The distance we had to look for was 10 to the minus 11, I believe. Nope, at a distance of 10 to the minus 14. So 10 to the minus 14 meters squared gives you 10 to the minus 28. So the total electrostatic force is something along the lines of 2 times 10 to the minus 46. 46 newtons. And look at UC. UC is the electrocoulomb potential between the deuteron atoms, which is 8.99 times 10 to the 9th. Don't mind the sloppy writing. I get sloppy when it's just computation times 10 to the minus 19, and this is just computation, but whatever. It's computation for your all's sake, not for mine. 10 to the minus 14 meters. And this is approximation of about 2 times 10 to the minus 13 joules, or 1.2 times 10 to the 6 EVs. 1.2 times 10 to the 6 electron volts. And how do you find it in the electron volts? Well, you have to multiply the joules times Boltzmann's constant for electron volts over joules, and that conversion, and you'll be able to get the new energy in electron volts. So, what does this tell us to do? What's the whole point? What's the point of this? Well, the point of this is that, Bittencourt's asking us in the second part of the problem, second part of 1.4, what temperature must the nuclei or the nuclei must have in a deuterium plasma. And the reason why there's a point to this is because plasmas must be of a particular temperature. A plasma, without the lecture, it would be difficult for some people to know, but a plasma is defined by its temperature. It's defined by its plasma frequency. It's defined by its Debye length, and those three constants, or those three factors, are all describe the same thing, that plasmas have to have a particular amount of energy in them. Now, plasma is typically a gas that has been energized to the extent that you have a separation of electrons and ions that are vibrating and that have an electric field and a magnetic field between them, such that they're highly energetic, and that after a particular amount of time they might settle back down to their equilibrium states of going back to gases. But they're highly energetic, they're highly energized, and so they have to have this extremely high temperature, or extremely high thermal temperature. And so when Bittencourt is asking us, what temperature must this deuteron plasma have if their average thermokinetic energy is to be equal to their electric potential energy? Well, this is easy to find out. First and foremost is that if you know, or if you have looked at my thermal physics book for thermal physics problems, and this is the reason why I've focused on thermal physics, plasma physics, and electrodynamics, is because for plasma physics, these three subjects are sort of essential, or the two other subjects, the thermal physics and the electrodynamics, are essential to really understanding and doing plasma physics. For one, if you looked at those videos, you'll realize that I talked about how there's a kinetic energy term in this 3/2 K Boltzmann T. This is a kinetic energy term. This is a thermal energy term. And it's not a kinetic energy, but it's a thermal energy term, a kinetic energy for a particle or a collection of particles. And if this thermal energy is going to be equal to the kinetic energy, which is going to be equivalent to this 1.2 times 10 to the 6 eVs, then what do we have? We have 3/2. This is the Boltzmann constant, and we have to do it in joules or eVs Kelvin, because this formula only works, this temperature only gives us Kelvin, or can only be used to find degrees in Kelvin, times 10 to the -5 eVs per Kelvin, and this is T. T stands for temperature, but we can easily find that the temperature is something along the lines of 9 times 10 to the 9th K. This is extremely hot. It's extremely hot. And that's putting it mildly. We can convert this to Fahrenheit. I can do that right now. It's the beauty of having a cell phone. I have the formula, but the formula's out of the book, so I'm not interested in doing that. But we look at, let's say 10 to the 10th. We're going to look for 10 to the 10 Kelvin to Fahrenheit. So 10 to the 10 Kelvin is 1.7 10 to the 10 degrees Fahrenheit. And the temperature of the sun (15 million degrees Kelvin). So temperature of the sun is 15 times 10 to the 15 million. So 15 times 10 to the hundreds, thousands, 10,000, so 10 to the 5 Kelvin, right? It's ridiculous. It's ridiculous. Lord, that's ridiculous. This is yeah, this is ridiculous, man. Yeah, this 8.6 times 10 to the 5, then multiplies that by 5. That's 10 to the almost 10 to the 11th. 1.2, and then you divide by 3, multiply by 2. That's ridiculous. This is 10 to the 9th. This temperature of the sun is 15 million. This is 10 to the 5th. This is 4 orders of magnitude greater. No, almost 5 orders of magnitude. 5 orders of magnitude greater than the temperature of the sun. So T over TS is 10 to the 5th. 5 orders of magnitude greater than the temperature of the sun. It's ridiculous. It's really somewhere along 4 orders of magnitude because this is a 15, but that's ridiculous. Shit. I didn't realize just how... I thought the sun was a lot hotter than that. Well, the surface of the sun is 15 million degrees. Lord, that's ridiculous. That just goes to show you how hot plasmas have to be, and how hot laboratory plasmas can be. I mean, this is the energy associated with 2 deuterium atoms at at extremely small distances. This is the temperature that they have to be in order for them to remain a plasma at that distance. It's ridiculous. And I'm astounded by it just because I hadn't done this particular calculation, but I saw this and I'm like, whoa, what does this look like in reference to something that I can actually those are the kinds of questions a physicist has to ask. What does this look like with respect to something that I know, or with respect to something that I can look up? And if you look up 10 to the 5th, and then you see that this is 10 to the 9th, this is ridiculous. This is either that this calculation's wrong entirely, which is a possibility. I give myself that. I mean, we'll go through it. 8.99, 10 to the 10 to the 9th. That looks about right. Because this has to be extremely small. It's 10 to the minus 38, and then this is small. This is 10 to the minus 28. 10 to the 38. This is more. This is something like 10 to the 10. 10 to the 28. So how is this 10 to the 46? Okay, so this is 10 to the 28. Yeah, see, okay, so already this gives you the opportunity to see that, okay, something seems off here. This has to be 10 to the 38. If this is 10 to the 10th, all this is 10 to the 10th. And this is 10 to the 38. This is 10 to the 28. 10 to the 28, add that. This has to be 10 to the 56 newtons. But note that this is repulsive. This is an extremely repulsive. This is extremely repulsive force because the particles are really close together and they have the same charge. So the force has to decrease until it gets to infinity. So it has to get bigger. So okay, so this makes sense. This makes much more sense. 10 to the 10 10 to the 28, I mean 10 to the 38, and then 10 to the 14. So 10, 38, so that's minus 28 plus 14. So this is looking right. This was looking wrong, but this is looking very right. And so let's say that this is 10, so 10 to the minus 6, minus 13, and joules to electron volts, 1.2 times 10 to the 6 EVs. That's the reason why we have a handy dandy cell phone, so that we don't have to do things like this. Ten to the minus 13 joules to electron volts. And actually this says this is about 6.24, because I got rid of the 10. I got rid of the 2. This is 10 to the minus 13 joules is about 6 times 10 to the 6 electron volts. So that seems right. Actually, you have to double it. So 1.2 times 10 to the 6, yeah. If it's 6 times 10 to the 6, so you multiply that times 2, it has to be 12, so 1.2. Maybe it's a 10 to the 7, so this might even be bigger. And then all of this is correct. And then it just comes down to the computation. And this has to get bigger, because if you divide 10 to the 6, 10 to the 11th, the 2 divided by 3, I mean, what do you have? I mean, you got a bigger number. You get something around 10 to the 10. At least 10 to the 10, 10 to the 11. And that's still bigger than 10 to the 5. Tens, hundreds, thousands, hundreds, thousands, 10,000s, 100,000s, and then you got your millions. These are 15 million. This is still humongous. So then you have to then you don't have to look at the typical heat of plasmas. And you know, the reason why I'm going through this sort of this sort of like research is because, I mean, if you think about it, if we can create laboratory plasmas that are hotter than the sun, has more energy, and we're gonna really have to like look into common plasmas. And this is, first of all, it's a deuteron atom. We're gonna go through that computation a little bit again, because I feel like that's going to be extremely important. But anyway, on to the next problem. That's ridiculous. That's ridiculous. This looks right. This looks accurate. Anyway, moving on. 1.7. So for 1.7, Bittencourt asks us to find the continuity equation of charge. The charge continuity equation goes like this. We'll derive it, not find it, but to derive it. And the way that I went about deriving it may be different from the way that other people have seen it, but this is the way that made the most sense to me. And you can, because these are fundamental equations, you can find different ways of deriving these solutions. You just have to find the one that's physically, physically appropriate. Yeah, told you I need my nightcap. So here we go. This is what I did. I said del cross B has to be mu naught times its current density plus epsilon naught time derivative of an electric field. And that I started with Maxwell's equations. So first of all, this time derivative of the magnetic field is sort of like, is not sort of, but it's a dummy current. Is it a dummy current? No, but there's a physical name for which they use that current. But we did this derivation in the graduate electrodynamics book. So the most logical thing is I look for the divergence of this sucker. And this has to be 0. This is a vector. This is a property of vector calculus. That the curl of some vector function, the divergence of the curl of some vector function has to be 0, and you can always prove that by going through the arithmetic. I'm not going to do that. I did that already. And so this has to be equivalent to m naught divergence of J plus epsilon naught divergence of the time derivative of the electric field. And because the time derivative is independent, the time derivative is independent of del, and del is independent of the time derivative, you can interchange the two. And so you can take the divergence of E and then take the time derivative afterwards. Doesn't matter the order in that case, because you're taking the operation of two independent variables. And for steady state solutions, this has to be 0. For steady state solutions, that has to be 0. Therefore, well, technically we don't do this yet, but for steady state solutions, it has to be 0. You have mu naught. But the thing is that we don't necessarily have a steady state solution because we have this extra term here. But I just wrote this down because in terms of magnetostatics, this would be 0. And for magnetostatics, this would also be 0. That's why you would get this. That's why you typically see this sort of formula, not this formula, but this form of Maxwell's equations in magnetostatics. So you have plus epsilon naught time derivative of the divergence of E, which is a function of position and time. And this has to be equal to 0. First and foremost, this here, despite E being a derivative of time, is still a charge density, or minus a charge density over epsilon naught. Except that this charge density is a function of position and time. This is Gauss's law. Gauss's law for a changing or a time-dependent electric field. And this gives you mu naught del of J minus d of t of rho RT equal to 0. And what is that, folks? There's your continuity equation. This is it. continuity equation, saying that the divergence of some charge density has to be equivalent to the current. The current charge density, or the change of the current charge density. Actually, what was that? Oh yeah, mu naught was multiplied by both. Yeah, mu naught is multiplied by both, so you don't have an extra mu naught term here. Sorry, I hated my notes, but that's not really true there. Easy peasy. Last one. Last one asks us to go through and kind of, prove a couple of Maxwell's equations. Well, one more of Maxwell's equations. We're already at 26 minutes in, so let's do this really quickly. We've already done it for the B field, so we've already gotten a continuity equation. We don't really have to do too much. This just had to derive it, and you can easily derive that from just an easy divergence of the Maxwell's equations for that extra dummy current, or that changing electric field density, or changing time-dependent electric field. So then we look at the cross of the E field. This is another way of saying Maxwell's equations for a time-dependent B field. This equation is more so suitable for electromagnetic waves, because in general, if you notice, the curl of the E has to be 0. Normally for electrostatics it has to be 0, but in general, for an electromagnetic wave, there is a time-dependent B field associated with the curl of the E field, because this is the vector that's perpendicular to E. And for the curl of E is going to be that time-dependent B field that's traveling perpendicular to the E field. And so what Bittencourt asks us to do is to derive that the gradient of B is a constant. This is our goal. This is what we want to prove. And so let's go about doing that. We're going to say that the divergence of the curl of E, in the same way that we did it for the curl of B, is equivalent to d dt divergence of B field. And we know that this has to be 0 because that is a a property of vector calculus. And simple enough that if this time derivative, or this divergence of the time derivative of B is 0, and you integrate both sides with respect to t, this says that the divergence of B has to be constant. But for our sake, a constant again, because it's a vector. This is a vector. Well, this is a scalar, but this scalar can be any constant. We just typically say that this is a 0 of the B field, or the divergence of the B field. Boom. And why do we do that? Well, for one, I guess if you think about it in a way, if you take, this is a constant, and you subtract by this word, let's say this constant, and you say equals 0, well, this constant can then be seen as, the divergence of B minus some function, phi equals 0. Well, this doesn't really change the B field at all. I mean, it kind of like shifts it a little bit. Just shifts the direction a little bit lower. just adds, it either, you know, pushes the zero up to a value that's more appropriate, or it, you know, it lowers zero down, or the zero of the B field down to something that's, you know, lower than something we can expect, and we can always change this. It's the reason why we don't really worry too much about something like a constant when we're worrying about vector value functions, especially derivatives and curls. Well, more so divergences and derivatives of those sorts of functions. But also, something else to keep in mind is that another argument for this is that we'll look at, this is the divergence of V. What does it mean to have a field that diverges? Well, if you take an electric charge, you take a charge Q, we have an electric field that goes radially outwards, and so the divergence of your electric field is according to Gauss's law, is the total charge enclosed divided by epsilon naught of some surface, some imaginary Gaussian surface around that charge. And for a point charge, then we take a sphere, because the electric field goes radially outwards. Well, let's do the same thing. We have some magnetic charge, which is really, in reality, it's a wire or a torus. For a torus, you get something like this. It's a very poor torus. Actually, I don't think that's a torus at all. It can be a torus. There you go, a torus. You have a torus, and then you have this magnetic field coming inwards, and you have this magnetic field coming inwards, and this coming inwards and inwards. So it goes out, and then it goes right back in to the surface, and it comes in at a different angle, and blah blah blah. But it cancels with another field somewhere surrounded, that surrounds this torus. The flux of the field cancels with another field line that's going inward and outward of this imaginary Gaussian magnetic field surface. And so again, if you take a wire, you have a current going that direction, or the B field is going around your current carrying wire. And if you take your Gaussian surface, well, you have a magnetic field coming out, but you have a magnetic field coming in at the same angle, and they cancel. All this is to say that there's no such thing, or well, not there's no such thing, but physicists have not found a magnetic monopole such that you have magnetic field lines just emanating from a source without ever converting back onto that source. Even on Earth, let's say that this is the planet Earth, we have magnetic field lines coming from various sources. Take the North and South poles, for example. It's not really that perfect, but if you take a Gaussian sphere around the two, let's do it in a black line. You have a magnetic field coming out and the magnetic field going back in. And if you look at even the fringe parts here, it gets really close to a magnetic field that's just very steep. It probably stays inside a Gaussian surface for certain distances away from the surface of the Earth, but we don't have, or we have not discovered any magnetic monopoles. Therefore, the divergence of V is constant, but more so zero, in the sense that all the field lines are enclosed or close on themselves for any magnetic surface or magnetic surfaces that we know. So there are two arguments for it. You can look at the theoretical argument, but then you can also look at the physical one. And I know that I kind of jumped into the physical argument because I just realized exactly what that could mean from a physical standpoint. But that's something that you have to kind of remember is that magnetic field lines are different from electrostatic field lines. For electrostatics, you can have things like a divergence because you have point charges ending on or terminating on their corresponding negative charge or other negative charges or positive charges, while magnetic field lines don't do that. Magnetic field lines, they terminate on themselves. They terminate on themselves, they attract and they push, they repel one another. But they're not doing it through work caused by some field, but by a difference in magnetic flux. So cool. Cool. That's going to be the end of chapter 1. In terms of like the major problems and the things that we definitely should know for moving on. Next time I'm going to do chapter 2 problems. Those deal with plasma frequencies and just learning about what plasmas are and all that good nonsense. I will see you guys next time. Thanks for watching.